So this is a research paper that caught my eye. It's called An Algebraic Framework for Hierarchical Probabilistic Abstraction. And it's put out by the University of Edinburgh. This paper catches my eye for a few reasons. Number one, and the biggest reason is that I can actually give the authors of this paper the real-world example that they lack within this paper. And so I'll get into that. But within this, I understand the problem that they are laying out, right? It's a problem within machine learning overall and for like mathematicians overall. The problem is that machine learning overall has both an algebraic as well as a probabilistic component. And the probabilistic component can be like calculus, trigonometry, etc. But you need to combine both elements. And then when you combine both of those elements, you lose explainability. And then so what would be ideal would be to have a pure algebraic model that would be purely explainable. Like that would be the unicorn, right? Is that if you were able to write the model 100% algebraically, then you would be able to explain the model no matter what. And then, but so it's like the unicorn is how do you get like probabilistic functions like calculus into algebra, right? And then like it's philosophical math, like math is very philosophical, right? And then so if you understand it from that aspect, it's more of like a philosophical challenge within that instance. And then like the primary question is does an algebraic extraction exist that can actually be probabilistic? And then so that's the there's two camps on that, right? It's either yes or no, and you can only side on one or the other on that issue. And then if there's no real world example of it one way or the other, if there's not a real world example of it that proves it, then we can't disprove it, right? And then so that's kind of where a lot of people stand overall with this. And this is a big a big philosophical question and debate within this whole entire framework is like, can you actually do this, right? And then if you dive deeper and deeper into these things, there's a lot of people that are starting to, as this paper lays out, believe that it is possible to do it, right? The mathematicians are citing more and more on the fact that it is possible to come up with an algebraic equation that would be fully explainable, even if it introduces probability. And then so that's what the authors of this paper do in essence. And so they do it mathematically. And then so they introduce three algorithms in order to do this. And then so their three algorithms individually and combined essentially do what they want it to do, like lay it out in this instance where you can essentially write an algebraic equation, have a probabilistic element within that algebraic equation, and then be able to fully explain that algebraic equation, kind of the unicorn. And then how they do this in very simplistic terms is that they treat probability in this instance via dimensionality, which is I've gone over this a lot recently in my channel, right? And then there's a reason why you see a lot of this research and a lot of this high-level research converging on all these same things, right? Just coincidentally. And then, but so within that, essentially, we can treat, let's say, like a wave function, a probability wave function, or something like along those lines. Anything that has probability, we can treat it via dimensions, right? And then within that, let's say like the perfect example that I think of in my head just immediately is flipping a coin heads or tails, right? That creates a perfect wave of probability, and then we can map that full entire wave. And I've done actually a previous video on this exact channel where I mapped that wave into high dimensional encodings, and then show that essentially in that instance I utilize HDC encodings to sample and predict probability essentially. And then so that's the kind of the same logic that they're doing within this paper. So within this paper, there's another concept that I've talked about extensively on this channel, which is abstractions, right? Meaning that these models aren't actually learning on your data sets, they're learning on an abstraction of your data set. And that's been proven over and over again now, right? So you take your data set, the model takes your data set, it creates an abstraction of that, like let's say a snapshot of your particular data set, a moment in time of the data set, and then it performs different functions on that snapshot, that photograph. It reshapes it, it changes the dimensionality of it. Dimensionality is extremely important within this overall calculation as a whole, right? And then so within that, these are all known. And then so what this particular algebraic framework brings into that equation is it says, okay, let's take this big broad abstraction, and then rather than treat the abstraction as a whole entity, what if we break up the abstraction into smaller abstractions? And then by breaking up the abstraction into smaller abstractions, then we can essentially create and build a building block of abstractions into the larger abstraction. And then so from there, if we took the base level abstraction, then we would be able to train up the whole entire abstraction. From there is the whole entire concept that they lay out here algebraically. It's a concept I've talked about this extensively before on my channel as well, where essentially I view this as taking a manual for how to build a car, and then taking just the bolts and then training a model on just the bolts, and then the manual related to the bolts of how to build the car, and then the model will then construct the car from there. It will be able to abstract, right? Okay, from bolts I need to add screws, and then from there it will add all of the different other metal pieces, and then they stack up hierarchically. And then if you understand and you're able to frame it in these hierarchical dimensions, then you can actually abstract and break down these abstractions into smaller concepts as they're laying out here very simplistically, right? And then so where I'll end with this is on this particular note is that I have a very strong suspicion that you would be able to do everything that I just laid out here within hyperdimensional computing itself as well. I will just simply leave that there as is within that, because the particular real world example that I built out here for this particular framework doesn't utilize hyperdimensional computing in this particular instance. I wanted to, first of all, understand the framework, and then secondarily, benchmark it against traditional Bayesian and deep learning models in this instance. And what I can tell you is that this ends up being a good model overall, right? So I have to work through it, and so I can see why they had some challenges with it, but especially for the authors of this paper, hopefully this is a significant improvement over their particular research here. It's a real-world implementation of their research. Again, within this particular research paper, it's all the mathematics and all of the framework behind it. I'll leave a link to the research paper, but what they don't do within this is provide any code at all or any real-world model, right? They leave that up to the future work within the paper, so here you go. And then so within this, I take their framework and their model, it's their math, right, within this. And then very first thing is very simplistically, can I do their math, right? So here it is. High-level decision to path selection to Turing navigation, and then we get essentially they come out as arrays, right? And then these are probability arrays, and then based off of abstractions of the original concepts, and then we can see that our probability arrays come out very simplistically 60%, 30%, and 10%, and then they're across the board and exactly how we would want them to be and very structured overall. So I can essentially employ step one of their mathematical concept and the framework. Cool. So step two, let me actually build out the model from there and then test it out. So I utilize a reinforcement learning framework. So I apply it into a reinforcement learning framework as my understanding of how it would best be utilized within a real world ML framework, as they state in their paper very specifically. So that's why I do that. I use OpenAI Gym in this instance, and then I go through, and then again it's that high level decision, path selection, and terrain selection and navigation. So I'm starting to understand understand their framework here a lot better, but my very first implementation of their framework is pretty abysmal, honestly. So what we can see is that deep reinforcement learning, I have a success rate of like almost 100%, 0.9999, and then Bayesian network is 84.8%, whereas my initial attempt at their method, HPA method, is 22%, and then taking double the steps that more than double the steps that the Bayesian network needed to do. So very bad overall performance, and then I chalk this up to my misunderstanding of the framework overall, which I'm glad that I did in my first test. So then I improved it overall. I run it through. I put like my first attempt was to like put my swarm. I put swarm algorithms into it just to see how I will do. Right. That's my first thought within that, just to see. And then very simplistically, it jumps it to 52%. So like just incorporating swarm algorithms into it, I can more than double the accuracy. But then I can't like more than double reduce the steps, right? So more than double, like I go up to 52% accuracy, but the steps I only go down to 7.9 as opposed to like 9.2 in the original one. So still more than Bayesian steps and still less than Bayesian accuracy. And then in this instance, then I essentially, last resort, go through and like fully optimize out everything that I can within all of this, realize that there's like more that I can do within like building out the like how these probabilities are functioning, and then how these agents are learning the individual abstractions of the probabilities. And I learned that like I go through and I'm like, okay, there's like some major errors that can be improved within that framework, right? So that I start to understand and I can adjust the goals that are being adjusted for the models and the model overall. I get a much more, like, by going through these exercises, by the end I get a fuller understanding of this HPA framework overall, this hierarchical probabilistic abstraction model, and then as you can see here, this is just, and this is without HDC. I think I could get better with HDC, but I get it up to 99.2% accuracy. And then my average steps are 2.5 compared to the deep learning of 2.2, but I'm blowing Bayesian networks out of the water, right? 84.8, and then 4.4 steps compared to my 2.5. My average reward, my numbers are just slightly below like deep Q learning in this particular instance, but the advantage that you would get within this is that it's fully explainable, right? Like this is using their algebraic methodology within this, so I'm proving it. Like here you go, authors, like it works. You can do it. It's pretty cool, and it gets you what you want out of it, right? Which is like the top level AI performance, but explainable. And then I'm sacrificing like the tiniest bit of accuracy, 0.999 compared to 0.992. So very like simple reduction in accuracy, very simple addition and compute, 2.276 steps compared to 2.502. And then so like again, across the board, we're just adding like the most minimal amount possible to this, but what we're getting is explainability out of probability, which is what you want, like the unicorn out of this equation. So to me, overall, this is a really cool research paper. It prompted me to build out that model here. I open sourced the model, MIT license, for anyone that wants to do whatever you would like with that model. It's fully built out, and you don't have to train it overall, right? It's simple to run here, and then you have it benchmarked out, and then so you can see their framework does benchmark out and beat Bayesian networks overall, which was my goal, right? I wasn't positive I could beat out deep reinforcement learning. I'm pretty sure I could at this point, like optimize it even further if I wanted to beat it out, but 99.2 compared to 99.99, I'm good. So if you like this type of content, please like and subscribe. Thank you very much.